that's the announcements. Let's get on with revealing the hand of God through physics. Nice way to introduce that. Except I have to say, my son had a grand debate with us. Sam loves physics and science. He had a grand debate with us about whether he ought to be able to bring his chemistry book with him to church. And he said, Dad, this is the way that God created the world. For me, this is worshipful. Well, honestly, I had to agree with him. And so there is one book that he brings with his scriptures to church, which is his chemistry book. Thank you, Karen. I'm glad you gave me that. And that's not physics, but it is seeing the hand of the Lord in creation. And we're glad to have Dr. Ware with us today. He has been a silent supporter of so many things at the school. I'm not going to read a bio, it's long. The first time I had, I guess, some professional contact with him was at the National Institute of Standards and Measurements. I think that's it, in Washington, D.C., where he was receiving, or where he was doing a professional internship, actually working postdoctoral work. He and his wife, Mary Kay. Mary Kay is a member of the Board of Trustees, and both of them have supported the school in so many ways for so long. I just saw a picture of Mary Kay in a 2000, I don't know what year that was, 2002 yearbook, getting her hair cut as a teacher in, what grade was that? In 5th grade, as she was teaching Little Women. Amazing. So this family has deep roots of giving heart and soul for the school for a long time. So without further ado, Dr. Michael Ware.
Okay, sure. And thank you all for all the work you do. My family has been a beneficiary of many of your teaching skills and your spirit. We appreciate that coming from you. So those of you who were here last year, I apologize. There's going to be a lot of overlap, but I think the things we talked about are important, so I'm going to do them or talk about them again. Let me get this going. All right. So today we're going to talk about how do you use the principal approach in science. And so I'll tell you a couple of experiences. So whenever I tell people I'm a physicist, I usually get one of two responses. I get told about how hard they thought high school algebra was and how they didn't really like high school algebra. Or the other most common result is, I really think that that's a cool subject, but I could never get it. And I think both of those responses are sad. And they go to this over here. So this is kind of a cartoon way of telling the difference between a physicist and then the regular people. So you come up to a knob and you touch it and you get shocked, and then a normal person would say, oh, I guess I shouldn't do that, and go away. And a physicist would say, I wonder if that happens every time that I pull a lever. We want to not cause shocks and all those things. We want to develop in our children this kind of respect and curiosity for science. I think that's wonderful. So you've all seen this for RAing. What we're trying to do is to research, reason, relate, and record, and this works in the sciences and in math as well as in the arts and literature and things like that. And I'm just going to go through the different areas here. I'm going to start with research and talk about how this happens in physics and how it can be related to what you do here at the school. So first of all, we're supposed to research and focus on primary sources. So what's a primary source? Okay, scriptures, good primary source. Diaries, right? So if you want to study the pioneers, you want to go read their diaries, right? If you want to study the pilgrims, you want to go read what they wrote. And so if we want to study physics, what should we do? Well, so here's the Principia Mathematica from Newton. So right, that's the primary source for physics, right? It's written in Latin, uses this really arcane notation of mathematics. Nobody uses this notation anymore. So is this the primary source for physics, for science? It's not the primary source. Okay? If we want to learn about the Pilgrims, we read their diaries because we can't experience what the Pilgrims experienced. We have to read about it. If we want to learn about the pioneers, we have to go read their diaries because we can't experience. But we do more than that. When we want our children to understand what the pioneers did, we take them out and we have them walk through Martin's Cove, and we have them actually try and experience some of the things that they did. So beyond just reading about what they did, and that's because with history, we're permanently and inescapably removed from the primary source. The primary source was people walking across the plains. In science, we are not permanently removed from the primary source. The primary source of science is the physical world. If you want to study the physical world, you don't go back and study Newton. Newton was some guy who studied the physical world. Yeah, he did it a long time ago, but that's not the primary source. We study the physical world. And so in the sciences, we're lucky in the sense that we don't have to harken back to some ancient text or something like that to get to the source. The source is right around us. It's the things that we touch and the things that we feel. And the kids can go directly to the primary source right in the classroom with things like popsicle sticks, and they can manipulate them and understand the physical world by going directly to the physical world. And so what are we studying in science? We're studying physical phenomena, tangible objects, things that we can touch and feel and manipulate. And it gets a little bit less true as we go on in terms of electricity and stuff like that, but in terms of what we study in elementary school, it's very tangible. Students can touch this. So the next R is to reason through and identify the leading principles of the subject. And so what are the leading principles of science? So I'm going to get a little bit abstract here today, but I think it's important and beneficial to kind of think about it this way. So the leading principles of science are something that we in physics or in other disciplines would call a model. So we have this curiously egg-shaped Earth here on the stage, and we have this thing that's incredibly complex. We have, cars driving down the street with, gasoline burning in them. All these things that are incredibly complex. And it's impossible for you to understand the Earth in all of its complexity. It's impossible for a physicist, it's impossible for anybody to understand all the complexity of the Earth at once. And so what we do is we make a model. So I teach a computational physics class, and we're going to model the Earth, the entire Earth, everything on it, all of humanity, all of animal life, everything else. We're going to represent it with two things. We're going to represent it as a position, and we're going to represent it as a mass over here. Okay? And then we're going to study its motion in relation to the sun. Okay? And so we're going to make this model of this point particle that has none of the detail and the complexity and the wondrous beauty of the Earth. Two numbers over here. We're going to model the Earth like this over here. And we call that a Newtonian model of the Earth. Is the Newtonian model of the Earth? Clearly not, right? We have abstracted and gotten rid of all of the complexity over here. So why do we do it? And the idea is, why do we model the Earth like this? It's clearly not a point particle. This clearly has a lot more features than just two numbers to describe it. Why do we do it? Right, we want to represent the most simple thing, the most simple idea that can represent the ideas that we're talking about. In this case, we want to study how the Earth moves around the sun. We don't care in this context, what's happening in China and how their traffic patterns are going over there. We want to focus down on the very simple and the most important part of the problem at hand. And so this is what we call extract from that something that's a principle. It's a concentrated little bit of truth. It doesn't encompass all the things that are going over here. And why do we do it? Because with this model over here, we can give interpretation to what's going on the earth. We can interpret, when I take this microphone and I drop it, I can interpret the motion of this microphone. I won't drop your mic, Grant. I can interpret that motion using just a couple of numbers, and then I can build up over time using this model a way to represent this earth that's useful. So I want to talk a little bit more about a model. So what's a model? Okay, so I like to use this. So my wife will tell you that I like organs. So I would really love to have one of these in my house, but she won't let me have one of these in my house. And so I want to have a model of an organ. And so, you know, to get a model of an organ, you have to go look at all of the different pipes and how everything works and all those sorts of things. And in the end, this is the only thing that my wife will let me have, this little piece, right? So this is a model of an organ, but it's really abstracted away from what a real organ is. If I wanted to teach somebody what an organ was, I would not use this. I would use this. Okay? So this would be, if I were trying to teach a student what an organ was, I would take out a water bottle. Okay, how would I use my water bottle as the model of an organ? Any ideas?
What water you might put in it?
Right, so I'd fill it up halfway with water. I'd blow over the top, and I would say, okay, so what I'm doing is I'm taking an enclosed container, I'm creating an air disturbance, and depending on the size of the container, I can make a noise. And the pitch of that noise depends on how the size of the container. And I would give every one of my students this model for the organ, and we would learn about the organ using this. Is this an organ? Clearly not. It's not beautiful, it doesn't sound very nice, it doesn't, doesn't play very well. But I do it because I'm representing the core nut of the idea with a physical model that students can touch, and feel, and understand. So a lot of you are elementary school teachers, in fact, probably most of you, and so I wanted to talk a little bit about another model that you do. Mathematics is a scientific model, okay? From kindergarten, you're teaching the children how to model. So what does that mean? So you'll probably throw up a picture like this, and you'll say, we want to model these apples. And then you'll write this crazy symbol over here, and you'll say, this is a model of these apples. Okay? In what sense of the word is that this little symbol over there, a model of these apples? Well, what you're trying to model is quantity. And when you teach the students this, you'll probably repeat a sequence of words to them, and you'll say 1, 2, 3, 4, 5, 6, 7. Then you write this symbol right here, which is a stylized version of an old cuneiform symbol that used to have 7 angles on it, but we've kind of stylized all the angles away. And you're saying, this is the model of these apples. And is it any wonder why some students get confused by that, right? So how on earth does this symbol model these apples? And so most students need a little bit more help than that. So you can also help them develop that model by using something like this. So this is also a model of these apples, right? So this is a model of the quantities. So you start making hash marks and things like that. And students need to be able to distinguish what it is that they're trying to model and get a representation for it over here. So it's not just science that requires a model, and it's not just math either. It's pretty much everything in life. So how many of you are musicians in here? Okay? How do we model music? Okay, what is music? It's this beautiful vibrations that transfer through air and have all sorts of, beautiful, nuances and stuff like that. But what do we use to model music? We draw some lines on paper, and we draw some little circles on the lines, and we say, that's music, all right? abstracted away all the beauty of it, all of the complexity and expression of it, to be these little dots on lines. Okay, and so that's not music. That's a model of music. And so you have to teach students, and it's important that they understand what a model is, and just keep it separate from the actual thing, and the reason why we do it, why we model. All right, so models are not the physical world. They give us a way to represent the physical world that represents specific parts of it, and they help us interpret the physical world. And this is not even related, exclusive to science or music. It's also what we do in the gospel. So in probably every house in LDS culture, they have drawn these 7 circles or 6 circles over here. And they say, and they've told their children, this is a model of the earth. Okay, in what sense are these 6 circles a model of the earth? Well, they give us a way to represent what's going on here. Over here we have this incredibly complex set of interactions with people and parents and good guys and bad guys, however you want to think of the earth. And we want to make sense of it. And it's not possible to understand everything and all of this complexity. And so we make a model. Okay? I'm not going to go through all the details of this, but it gives us a way to represent what's going on here on Earth. And it gives us a way to interpret the things that we have going on around us. Because we have a framework that is simple enough to understand. Is this real? It's real in the same way that Newton's laws are real. It represents a simplified version of what goes on here in life, right? If you think about the incredible variety of circumstances that everybody's going to go through, this is obviously a huge simplification of what the plan is, if you think about it that way. But it's useful. So what do we do in science? So in science, we firmly believe that there are some laws. Scientists don't make, science per se doesn't make a claim that those laws are of divine origin, but in LDS scientist, as I am, I would say that those laws are of divine origin. We have laws that govern how the universe works. We don't know all the laws of nature, but we can build models to explain physical phenomena, and our models are pretty good. And we have a pretty good idea that we know some of the laws that govern the physical universe and how it gets put together. And the goal with a model is understanding, and I always like to couch it in this way, that we want to be able to predict the future. So how does a model help us predict the future? So I like to use the example of Apollo, the Apollo rocket program. So back in the 1960s, we put 3 people in a little capsule and strapped them on top of several tens of thousands of tons of explosives, and we had every expectation that a few weeks later they would arrive at the moon. Okay, how could we make such a prediction? Well, it's because we knew some principles. Okay, they used models that are known to be overly simplistic, that don't actually capture all the detail. They use Newtonian physics, which since we've known about relativity, we know that Newtonian physics is incomplete. But they used it nonetheless, these simple models, and a few weeks later, we had astronauts around the moon. The same thing goes with other models. If you think about the model of the plan of salvation, what are we trying to do? We're trying to understand if we do these certain things, this will be the result. We're trying to understand the relationship there. All right, so how do we teach students about models? So this is how textbooks typically teach about models. So if you read a textbook, it's you're like sailing along, and you look off in the distance, and I see Newton's second law, and over here I see the laws of chemistry, or the model of chemistry, and it's something that's presented as if it's something just out there to discover. This does a great trying to teach science in particular. Models, I'll go back here. Models are things that we create. And specifically, every individual has to create the model again. The laws are something that we believe are fundamental and out in nature, but a model is something that you have to create. And specifically, a child has to create the model of the world in their head. They've already started doing this. Everybody in here has created a model of the world. You have in your brain a model that says, this is how cars work, and this is how doors work, and this is how my interaction with people work. You created a model in your brain, and you didn't discover it, you built it. And every student has to build a model of how the world works. They have to build a model of how doors work, how balls fall, how interacting with other people works. And it's a new creation every time it happens. And this is what we call in physics modeling. When we teach students physics, or if you teach them chemistry, or if you teach them math, what you're teaching them is trying to guide them through the process of creating in their brain a model that represents the physical world. It's not the physical world, but it's an abstraction, and it's simplified, but if you wanted to get it to be correct in the sense that it can predict the future and help them interpret. How does creativity come into this? So the cartoon here kind of summarizes it. So I expect you all to be independent, innovative, critical thinkers who will do exactly as I say. That's sort of how we teach school, right? You know, you're supposed to be independent and creative, but if you give the wrong answer on the test, the one I wasn't thinking of, you're wrong. And so there's value and validity to both of this. When we teach science, what we're doing is we're trying to take the model and hopefully, so there's two different models. So there's this, in science, we've taken our model of the world and we put it on the table, so to speak. And science has the luxury that we can do this. We can take our model and we can write it down in papers and we can hand it out to our colleagues and they can look at it and they can see how well that jives with their model of the world. And also they can compare it to experiment. Other disciplines don't have quite the luxury we have in science. They can't compare their models to an experiment to see if they're valid or not. They don't have that test. But once we've, as a community, come up with a model that works, we're trying to get the students to build that specific model in their brain. And so whereas with art and music and some of these other things, it's encouraged and wonderful to have students have, different models of how the different things can work. In science, we're a little bit less creative in that, well, I won't say less creative, but we're a little bit more, we want to create a model that actually conforms with what actually happens in the physical world. And is at the college level, we have a challenge in that everybody's created a model of the world already before they get there, and most of them have created an incorrect model. And so about half of what we do in college physics is to try and beat out of them this incorrect model that they've created. And it would be so much nicer and so much more helpful if from kindergarten they start building correct models rather than having to beat out of them this incorrect model that they've accumulated over time. I'll skip that, it's another cartoon. But so this is a guy who thinks a lot about how people learn science. His name is David Heston. A lot of the stuff I've talked about comes from him. So this is not just for physics. He teaches in the context of physics, but it's all of science, and I would contend most of what you do here at American Heritage. So each student, each individual must literally reinvent the Newtonian world in his or her mind and understand it. You have to reinvent this model in every child. Every child has to do it for themselves. You can't just place it in their brain. They have to invent it and construct it in their own brain. That's a creative act of high order, so it's no wonder that students find it difficult, especially considering the fragmentary presentation that Tony and Fury textbooks. So that's specific to his specific discipline. But keep in mind what it is you're trying to do when you teach children math and science, is you're trying to help them build a model in their brain. I'm going to skip over this one. So it's important when you teach modeling, teach science, that you help the students understand the distinction between a model and the physical world. So these are ice crystals, quite beautiful, although squashed in aspect ratio. And we make this model here. I don't have a physical model with me, but we draw these things with balls and sticks. And we say that's what ice crystals are. Okay? And if you don't teach the students that this is an abstraction, a model, it's a representation of the ice crystals. But if you go down and look at the microscopic level, you don't see little sticks and balls, right? So this is an abstraction, and if you don't help children understand the idea that we're creating models which represent the physical world, which are not actually the physical world, if that makes sense. So they need to keep a distinction between what is the model and what we're trying to represent. And so, let me go back to this slide now. So, what are we trying to do? So we have, in science, we have a model over here. In this case, it was Newtonian physics. It could also be chemistry, it could be mathematics, all these kind of things. This is an established model. It gives us a representation of the world and allows us to interpret the world. But it's over here, and they have to create it in their brain. And so what happens? They interact with the physical world, they perceive it, and they interact, and they try and build a model. What we also want them to do is interact over here, and they have to create in their brain the model, and that will give them some understanding to help guide their perceptions. And this is an iterative process. They found that it takes at least 10 times of being confronted with a misconception in physics for them to really believe that what they were thinking was wrong. So you ask a student a question, and they think it through, and they give an answer that's based on the incorrect model that's in their brain. And we say, no, that's wrong. This is the right answer. And what we found is that they don't believe you. Students have this, built-in model of how the world works, and they don't believe you until they're confronted multiple times with the reasons why that model that they've constructed in their brain isn't accurately representing what's going on in the physical world. It takes multiple times.
Would that change? I guess.
I'm not qualified to answer that. So the question was, would it change if they're younger? And my guess is that it would not. That even by the time they come to you as kindergartners, they've already developed a physical model of the world. They in their brain, they've developed a model of how doors work, and how walls work, and how all these things work. And it takes a lot of confrontation of the reasons why that actually isn't how a good representation of the world works. But to get them to believe that that's not the case. Yeah.
Well, I've seen that in my work. It's really quick if I give an example. If you tell a student to put an apple in the room, turn off all the lights, at some point you'll be able to see that apple. Well, they believe you can at some point. That your eyes are used to the dark, but if there's no light coming in, you'll never, ever, ever see that apple. And that's a concept that's hard for them as little kids to understand.
takes a lot of work to build a model like this. And so students can get easily frustrated with that work. And even professors get frustrated with that work. So what are some take-home points? So teaching by telling is ineffective. If you just tell people things like I'm telling you now, so bad modeling of how you teach. If we just tell them things they don't believe them, it doesn't really work that well. If you're not careful, students will try to memorize algorithms rather than learn principles. This is especially true in math. So like I mentioned in math, so we write this crazy symbol and we say that represents this quantity of things. Through addition, subtraction, multiplication, division, the math facts is what they call them, it's possible to memorize all of these things without having any clue or any good physical model in your brain what you're modeling. And then you start getting to something like algebra, and there starts to be so many rules that it's no longer possible to memorize by brute force all of these facts. And that's when people start to run in the wall, because as they went through elementary school and learned all of these math facts, memorization, by rote memorization, they never in their mind built the model of what they were representing. And so it becomes very difficult for them to transition into this higher or more complicated model of way of thinking if they haven't actually realized what numbers represent and how they work. And so it's really critical, especially at the early stages, to help them not just memorize math facts. The kids that you're going to get it right, they can just memorize, most of them can memorize by rote memorization, all the multiplication tables, all the times tables, all the addition and subtraction facts and stuff like that. They can memorize those algorithms without learning what they're modeling. And it'll catch up to them if that's what they do, because they won't be able to abstract further if they're just by rote memorization trying to brute force memorize math. Because you can't, once you get to algebra, you can no longer just memorize everything once you get beyond a certain point. You have to have in your mind a model. When you say words to your students, those words do not elicit the same images in your students that they do to you. So when I say something like work to you, most of you, it elicits a very different response in your brain than me. When I think of work, I think of a force acting on an object over a distance and it's related to energy. When I say work to you, you're probably thinking of going out and weeding the garden or something like that, right? And so the same thing happens when you use words to your students. You tell them a word describing a concept, and you have a model in your brain of what that word means. And to them, it totally misses the point. And so words are often ineffective ways of communicating models to them. The other thing is that watching a teacher solve problems is a particularly ineffective way for students to learn how to solve problems. It just doesn't really help a student that much to watch somebody else solve a problem. Maybe once just to help them get an example, but how do they really learn? They learn by solving problems. Okay, so you actually have to do it yourself to learn things. So constructivism is the fancy name that they give this. So constructivism is this idea that you are, each individual, each student is in their brain having to construct a model of the particular subject. In this case, it would be science. You're having to construct a model in your brain of how that works. And I'm going to skip over this just in the interest of time here. So
let's just think about math. So how do we usually teach math? Well, you give a student this big sheet full of, symbols, and you teach them when you have a symbol 3 and then this little cross and then a symbol 5, that algorithmically comes out to 8, right? And we give them this big sheet of symbols, and they learn the algorithm to do that. But are they really understanding the modeling? Are they really understanding that what we're doing is we're taking a quantity of things, we're adding another quantity, or putting another quantity of things with them, and we're asking the question, how many altogether things do we have? If they don't have that really firmly in their mind, then solving a bunch of math facts is not going to be that. I mean, they'll do it, they'll memorize it, and eventually they'll be able to spew out the answers. But will they have in their mind the correct model that will allow them, as they go on to more advanced math and more advanced ideas, that they can build on that model rather than just trying to memorize another algorithm. And so if you can just think of models as a basic unit of knowledge rather than a problem-solving skill as a basic unit of knowledge, it can help. Science is hard because you have to build it over a sustained period of time. So over here we have set theory. You take different groups of things and you put them together, and that's something that you might do in first grade. Over here we have particle physics, probably the hardest branch of physics. Particle physics is just set theory. When it comes down to it, it's a mathematical representation of set theory, and it's built on a lot of the same ideas that they're going to get in kindergarten. But if they don't start building that model and start building it accurately from the time they're young, it's really hard to get to an accurate representation or a useful representation when they get to the end. All right, so how to do it. So constructivism versus transmissionism. Constructivism is this idea that we're trying to, in their minds, construct a model. Transmissionism is the idea that you're trying to, as we jokingly refer to it in college, we're trying to transfer the notes from the teacher to the student without the content going through the brains of either, right? So that's the transmission approach. So constructivism works well by cooperative inquiry, by students physically doing things, by giving them popsicle sticks, having them represent numbers, represent quantity, adding, subtracting, dividing with physical things, rather than telling them or demonstrating. So that works better. So always student center on the student, not what you're saying, but what the student is doing. Active engagement almost always works better than just sitting there listening. Student activities, physically doing something, almost always works better than even you demonstrating something. So if they can get their hands on something, especially in physics and science, it's important. Student articulation. This comes to notebook writing. If you want the students to understand something, have them articulate it. Have them verbally tell somebody about it. Have them write it down in a notebook. Have them articulate it in their own words. And further, once they've articulated that, the beauty of science is that once you've articulated something, you can then share it and together look at this thing that you've articulated and see if it's right. And so have them also evaluating each other on that. So lab-based is much better than textbook-based. It's a lot further. All right, so there are model development activities and model deployment activities. So development activities are where you're trying to get them to build models in their brain. Deployment activities are where you're trying to get them to apply it to a new situation. So I'll skip over that. I'll end with this slide here. So one of the sad things about science, in my estimation, is that once the students leave this school at 12th grade, they would probably never have a real science class again. When they get to BYU, we're going to run them through something called Physical Science 100 and maybe Biology 100, which are these super high level, hydroplane across the surface, kind of courses where we're just gonna try and help them appreciate the flavor of science. But in high school is the last time that they're actually going to do a physics class or a chemistry class where they sit down and they solve a problem. And so sorry to put some heavy responsibility on you, but you're it. We're not going to catch them in college because most of them are going to go on to business and music and something else where they're not required to take any more science. And the skills that you get in modeling, learning how to model the physical world in science, are broadly applicable. They are not narrowly applicable just to science. And so if you can, at this level, teach them those modeling skills, then you'll have done a great favor. And the last thing is speaking English. It's really easy when you get, especially as you get into high school, this may more towards the high school, is to speak in this language we call math and stuff like that. Students don't know that language yet. Speak to them in the language that they know and using terms and ideas that they're already familiar with. I think I'll stop there and thank you for letting me come and thank you for all of you here